Hello, welcome to the Moab Science Festival's virtual star party. Today, I'm Crystal White, the Associate Director with Friends of Arches and Canyonlands Parks, and today we'll be talking about where elements come from and how did they form to make all the wonderful things that we have around our universe. And the festival will be going on through Sunday, actually, so get out there and enjoy some science. All right. We'll start with talking about the cosmic microwave background. Like, what is that? There were a couple of radio telescope astronomers from Bell Laboratories that were trying to find some signals in space, specific ones, Wilson and Penzias with Bell Laboratories, and they kept picking up static. And the static was really, really frustrating to them. And so they went out and they're looking at the telescope and they're trying to think of everything around the center that could possibly be giving off static, but they can't find anything. And then they see pigeons on the telescope and they're like, well, maybe we should clean off the guano and get rid of the pigeons. So they clean up the guano and they scrub down the telescope, and then they take the pigeons and transfer them to another location. And they're still picking up the static. And so then they ask some other radio telescope operators, astronomers, are you picking up this same static, this radio static? And they're like, no. But they knew what they were picking up. And they started describing all atmospheric static and all these things. And they realized that what they were picking up was what we call now the cosmic microwave background, which was the sounds of the very early universe. There's a few seconds a few thousand years before that of things building, but they're picking up the first sounds of that expansion of the early universe, which happened very quickly and very rapidly and was very heated. So that's the farthest back that we can hear in our universe. And after that period, well, I'll just go to the next slide. We don't really know what happened before the inflation of our universe. We still call it the Big Bang, but every astronomer agrees that there was no big blow up, no explosion. It was more of just an inflation. And within the first seconds, you start to get protons forming. But before that, quarks have to form, because that's what protons are made up of. And so you've got basically this hot, uniform area that is heated in the universe, and protons begin to form out of quarks. And then after you get protons, you start to get neutrons forming, and then you start getting nuclei forming. And eventually, you start to get, and then there's electrons floating around as well. And so if I go back, what we call the dark ages is basically when all those electrons are floating around in the universe, but they haven't connected to anything yet to make the first atoms. And so you have quarks turning into protons, protons eventually turning into protons and neutrons in a nuclei. And then eventually it cools enough that those electrons can start to attach and we get the first atoms. And so after that started happening for a little bit of time, you start to actually finally seeing light, because those electrons are no longer free roaming cloud. They're being attached to atoms. And you start to get the first hydrogen elements. And then eventually the hydrogen elements start crashing into each other to create helium elements as well. And then you hear the cosmic microwave background, which sounds a lot like static. So here we have an hydrogen atom that's the most simple element. It's a proton with an electron cloud. And as they say, never trust an atom. They make up everything. I'm just kidding. But they do make up everything. but you can trust them. And it's kind of fun to sit and think about the atoms in your body. We always think when we're touching something, we're touching that item, we're touching this book, or we're touching this glass of water. No, we're actually, well, we're touching the electron cloud of that. So it's kind of fun to think that you're touching the outer cloud, but never the nuclear, never the core of the atom. And so as those first elements began to be created, you started to get an increase in those atoms creating matter gathering together. Matter just always wants to gather together in the universe. And so you start getting star formation. And then eventually the stars gather to get galaxy formation and planet formation. And then you have dark matter in here as well, and dark energy speeding up the expansion of our universe. Anytime you look at a nebula cloud that has matter in it and is a hydrogen cloud, you start to get that matter wanting to coalesce, to come together. And as it does that, you start to get an increase in temperature, and eventually that matter coming together and forming what we call protostars, which are the precursors of actual star formation, which is what this is showing here. The yellow that's lighting up around the red here are actually like protostar here, protostar here, protostars here. And those stars will flatten out that area that is around them immediately, like this. And once that core and enough matter has, and energy and heat has started in that core of the protostar, nuclear fusion takes place, which is hydrogen converting into helium through fusion. And that outer disk that you can see, all of this area, starts to form planets and asteroids and comets and all the stuff that we find in our solar system. And here's a little simulation of that happening. You see that matter come together. It starts to flatten out in a disk, and you have a star formed. Boom. So some of the most beautiful objects I've found to look at in the night sky are what we call stellar nurseries. And that's these hydrogen clouds of gas and dust and matter out in space. And so here's the Lagoon Nebula, which is in the constellation Sagittarius. And you can see that there are stars forming. And it's definitely got a bright star right here. And this is the Trifid Nebula, also in Sagittarius, which is also a stellar nursery. And in Orion, one of the most beautiful stellar nurseries that I know of, which is the Great Orion Nebula. And this is actually in our morning sky and will be center stage during the winter. So this is our sun, Sol. And Sol is what we call a low mass star. It's a very small star compared to the giants that formed right after the inflation of the universe. And those giants were necessary to have the building blocks for the atoms and life and everything around us. The 92 natural elements that we know of. But Sol, once it started its life, began fusion, hydrogen into helium in the core. It'll burn happily like that until the hydrogen burns out of the core and it's all helium. And stars just want to turn hydrogen into helium. And so at that point, it'll start seeking hydrogen in the shell of the star. And as it does this, it kind of puffs out like a marshmallow over a fire. And it puffs out. When our star Sol does this, it will most likely consume the Earth. And as it does that, it kind of pushes out pretty hard. And you start to get that expanded, puffy star, and it starts to cool. But the core is still very, very hot. And in the last little bit of time on these stars, it'll push out, and then you can get the creation of carbon and oxygen if the star is big enough, as it pushes the shell away. So really, to understand this, there are two major forces in a star working together. You have nuclear fusion from the reactions, the fusion in the core, pushing outward, and then you have gravity pulling inward. And those two forces, when they're in balance, when there's hydrogen burning into helium, everything's calm. The star's happily just creating fusion, creating helium. But the second that those become out of balance, like when helium is starting to convert and hydrogen is burning in the shell, that's when things change. So with a small star like our sun, it goes from that protostar phase to the star phase to the red giant phase we talked about. And when it pushes its shell out into space, it's called a planetary nebula. And planet just simply means wanderer. So it's a gas cloud that's wandering through space. And eventually, it'll leave the white dwarf behind. And it all started in that nebulous gas. In the constellation Ursa Major, or the Big Bear, we see the very cute Owl Nebula. So this is all gas from the shell of that star. So this is a planetary nebula. In Vega, we find the Ring Nebula. And the Ring Nebula is one of the most beautiful planetary nebulas I've ever seen. It's gorgeous. It reminds me a lot of a fuzzy donut floating out there in space. And in the constellation Vulpecula, you have the Dumbbell Nebula, which is very bright. It's actually quite close to us. It's 1,300 light years away. So relatively close and very easy to see. You can see it, I believe, with binoculars or a low-powered telescope for sure. And occasionally, white dwarfs will supernova, but they have to steal gas from somewhere. So most stars come in pairs. They come in binary pairs, which means they are actually bound to each other, and they orbit a central point of gravity between the two of them. And if one has become a planetary nebula, shed its shell into space, and it's now a white dwarf, if the neighbor star is probably similar age, starts going through this while the white dwarf is still hot enough, that white dwarf, as it puffs out in its red giant phase, if it gets close enough to the white dwarf will actually steal the shell of hydrogen from around the second star. And eventually, it will supernova, which is what you see right here. This is called a type 1 supernova. This is the Cigar Galaxy. And there's quite a few of these. And when you get a type 1 supernova, it does create quite a few elements, but not as much as the next type of star we're going to talk about, which is a high mass star. So this is any star that's more than 10 solar masses, and a solar mass is 10 of our suns. So it starts out the same with the protostar, the massive star, the red giant phase, and then something different happens. And you get a supernova, which is a complete explosion. And you're either left behind with a hot neutron star that's super magnetic and energized and dense, or if it's big enough, you'll get a black hole. So this is if you could look inside of a high mass star, this is what you would see. You would see hydrogen fusion into helium for a long, long time. And then after that red giant phase, you start getting the carbon and oxygen. And then as its core is so big and so hot at this point that it goes on to further produce magnesium, neon, oxygen, silicon, sulfur, and then eventually iron. And iron behaves a lot differently with nuclear fusion. It tends to want to absorb energy more than to go into another fusion. It takes a lot of heat and energy to create more fusion, because what will happen is instead it will collapse and implode the star, because that gravitational force from the core of the star, this giant core, will crash the star and it will implode and then explode and release the other 92 elements that we know that naturally occur out in space. Now, this is the star Betelgeuse. And Betelgeuse is a lot of fun right now. If you ask astronomers, which star do you think's probably the next likely candidate to supernova, they'll tell you Betelgeuse. And this last winter, Betelgeuse kind of gave us all a little bit of a heart stop. We thought we were going to get to see a supernova in our lifetime. It was super exciting. And then it got bright again. But Betelgeuse is usually one of the brightest stars in the night sky in the winter. And it was pretty dim this last winter, dim enough that I could even see that it was not quite itself. And they started to see a lot of activity in the star as it dimmed. But then toward the end of winter, it actually brightened back up. And they were like, oh, it'll be another 10,000 years before it dims down. Well, that's not true. It's starting to behave funny again. So there's still hope at seeing that supernova of Betelgeuse before I die. And that's much like what it would look like for a giant star to implode and explode. And when it does this, the light that will come from that star will be brighter than a nuclear core from a galaxy. And we know this because we've seen it out in space. We've seen how bright these supernovas are, and they shine equal to the nuclear core, which is usually, billions of stars in that nuclear core. And so here's a neutron star that's could be left behind by, a medium-sized massive star, whatever that means. And these things are super dense and super magnetic. They have a huge magnetic field. Sometimes they'll be spinning and putting off radiation on both of the poles, which is what we call a pulsar, and you'll get that searchlight. But if you were to take a spoonful of this neutron star, you would end up with a weight heavier than all of humanity in that one spoonful. They are super dense. And if the star is massive enough, it will turn into a black hole. Black holes are interesting. We always thought a star had to supernova, implode, explode to create a black hole. And it's been observed in the last couple of years that there was a star massive enough that it flipped straight to a black hole. We never saw an explosion of any kind, which is incredible to think about, something being that large. Well, one of the fun things to look at is the remnants left behind by these supernovas. Here we have the constellation Taurus, which is also a winter constellation or an early morning constellation at this time. And this is the Crab Nebula that was left behind when the star exploded, supernovaed. And we know that this happened in 1054 because we have historic recordings of it from the Chinese astronomers. And we also have a recording south of here in Chaco Canyon in the form of a pictograph. So here's the crescent moon. And we believe this hand is pointed in the direction that the supernova happened. And here is the star. And you can see that they've made the star almost as big as the moon, because it will outshine the moon for a while. And so in 1054, we believe that this was created by the Pueblo people that inhabited Chaco Canyon. And so it's a nice visual sight as to how bright a supernova can really be. In the constellation Vega, or not Vega, sorry, Cygnus the Swan. I saw Vega there and said it, but this is Cygnus the Swan. And in the constellation Cygnus the Swan, we find another supernova remnant, which is this beautiful Veil Nebula. Now, when you look through this, I look through a telescope at this, it does not look so colorful. Cameras can pick up color that our eyes cannot at night, and so it would be more of a gray wisp going through the telescope view. But it's always amazing to me that you can see these things. You can see these clouds of gas and dust that are left behind by supernovas. The things that create all the elements that we need for life, other than hydrogen and helium. Those are created in the initial inflation. Although they are created tracely occasionally now. And it's fun to think about water. I'm drinking atoms that are about 13.7 billion years old. Kind of blows my mind sometimes. And the atoms in me have been recycled in the universe many times before they became part of me. And when I leave, they will also be recycled back into the universe. So here is the periodic table based off of the elements that are created. So in the Big Bang, we get hydrogen and helium, a little bit of lithium. In cosmic ray spallation, you get beryllium and boron. Low mass stars, you get carbon and nitrogen. And exploding supernovas, you get all the way up to, I don't even know what RB stands for. I should probably know that, but anyway. And then exploding neutron stars will get you all the way out to here. Now, these we know exist because of nuclear fusion reactions. They were not naturally found here on Earth, but that's how we know that they exist. So we get up to 92 naturally occurring elements that we see here on Earth. And we have not found any element out in space yet that is not naturally, that doesn't fit those 92 elements. There's a theory that maybe neutron stars have elements that we are not familiar with. But I always like to think about those elements showing up in the natural world around us. You can see here, the sandstone has two different colors in it. And this is the element iron. There's iron pigment in these rocks. And once oxygen touches the iron pigment, it oxidizes and rusts and makes that beautiful red color that Moab's known for. The white sandstone has just had water strip those pigments out of it. And you think about the soil crust, it's all around us. It's a champion of fixing nitrogen in the soil for desert plants to use to grow roots and become strong. And my dog Mesa, she's mostly made of oxygen, just like I am, but she's also made of carbon. And here she is, this little lovely life form of carbon running around on the sandstone. And us, we're 65% oxygen, 18% carbon, 10% hydrogen, the initial element created in inflation of the universe. We're 3% nitrogen, and then everything else. We come from all of that forming, from the hearts of dying stars. And it's always one of the best quotes I've ever read in my entire life by Carl Sagan. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interior of collapsing stars. We are made of star stuff. Well, I'd like to thank you for attending this session of the Moab Science Festival this year. And here you can see the schedule for what's left. I believe today is Saturday. This is a post recording of the presentation. And we have the Harvest Festival coming up, the dinosaur exhibit of the new dinosaur that was discovered in southern Utah, which should be incredible, tonight at Old Spanish Trail Arena. And then tomorrow we have a bird walk, a bio-soil crust hike, an invasive plant hike, and science trivia night. Should be a fun couple days. And I hope you've gotten out and enjoyed some of the festival already. But thank you so much for attending, and have a wonderful day.